I got 3 years so far. Maybe we'll have a few more. Appreciate you coming. Okay, we are recording. Yeah. Oh, anything before I share the screen? Okay. All right, here it comes. Eventually. Trust. Hold on. I don't know why I won't share. Oh. Okay. Sorry. Cord got taken out. Nice to see it. Just trying to share the screen. Let me try it again. Try one more time. Share the screen. Okay, now so Tuesday. Black and blue. Now I checked the porch after I got home, and I put out the folder before I left in the morning. So I'll put the folder out. It'll be out there by 8:30, latest in the morning, 8:30 a.m. And then it'll stay there till probably 9 p.m. So 12 hours, it's out. The folder of your papers is out there on the front porch, 812 Carriage Lane. So come by and get your test. I mean, if you got a 270 or a 300, check the key. If you got that, then maybe it's not worth for you personally to do black and blue, but you probably want to look at it and see what you did miss. And then you'll put it back in, you'll grade it with this video key, and then you'll put it back in that folder. Theirs is due Thursday, so yours is due Thursday too, by 6 p.m. for you. Well, for them too, they could bring it by the house. So by 6 p.m. Thursday, you return your test back in. All right. But on this is a 52-minute video. This video key, a 52-minute video where I just kind of go over the key. I don't really rework. I started reworking the problems, and that was going to be 2.5 hours. And I didn't have that kind of time. No one's going to sit through a 2.5 hour video. So it's 52 minutes. It's long, but the key is already there. So if you just want to kind of fast forward so you can see the key, it's me talking about it, why I graded the way I graded, what I'm looking for here, what I'm looking for there, why you might have missed something. So we're still talking about, and this is sort of the international symbol for constant acceleration. Today gets a little hairy, so I appreciate you all being here. But the constant acceleration forms what's called the trio. And today we'll actually get into the quartet towards the end. And there's quintets, there's sextets, it goes on and on. But for reality, 95% of motion in your world on a daily basis is either solo, duet, trio, or quartet. We call that. This is the ball rolling down ramp, first hour, second hour, third hour, and virtual. This is you guys as well. So we've already done a trio in detail, but I know from experience that once is not enough for you to understand it very well. And we've also talked about different orders. When I say third order, I mean T. This would be like T to the third, T squared, or it could be X to the third, X squared, T to the first, T to the zero, T to the negative first. So these are the orders of motion. Most of the motion is going to be somewhere along. Okay, so now every hour has their stuff just squeezed down, so I don't have to keep erasing and redoing it. question really comes down to this for the first half of class today, and that is, what is the acceleration of this parabola? I asked a while back, I said, what's the slope of this curve? And that's a dumb, nonsensical question, because we all know that on a parabola, the slope keeps getting steeper and steeper and steeper as time goes on. But it is a legitimate question to ask, what is the acceleration of this parabola? In other words, if I want to boil this parabola down to one number, so good for your notes here. If I want to boil it down to one number, first time I've ever taught it this way, so I like what would that number be? Like we take, okay, how about temperature? We say, well, it's 72 degrees outside. That's putting a lot of motion into one number. There's a lot of Brownian motion in the air, right? Am I lagging here? Am I laggy? I'm sitting here right at the router. Come on, man. I can't be laggy. I look like I was lagging. If I get too laggy, you guys, I'm not looking. I can't see the daggone. You're gonna have to tell me. I can't see the chat. I don't have room for it. Well, okay. I'll find room for the chat. You're extremely shy. Chat. All right. So although the temperature is 72 degrees, that is like an average. But it's one number that tells you how all that Brownian motion of air molecules hitting your face, your arms, and your legs, how the speed, sort of the speed limit. Okay, so one number tells you a lot of things. Well, same thing here. I want one number to tell me, or you could say it this way: what number represents the curvature? Sorry, turn it off. What number represents the curvature of that parabola? That's what first half what we're trying to do. So yesterday we did this much. We might have done a little more, but I erased everything because not everything, but I erased it down to this beginning place. So we said, okay, there's my curve. I'm going to go through and I'm diagnosing it, and we're doing what Newton did. I'm going to take each little part of it and find out how the slope is changing through time, through the 9 seconds. Okay. So then we come down to this graph and we said, well, these are the secant slopes, and so it's like a step function. We said because this, by the way, is the essay question on the take-home test on number 7D. I think there's an essay question. It's asking you, how can you say that these yellow segments, how can you all of a sudden turn those into points? That kind of goes against every geometry proof there is. A line equals a point. No, it doesn't. So how can you say that? And it comes down to this. Remember we said that, and I made them tell me in class, but remember we said that any kind of parabola, just x equals t squared, you can do the secant, and the secant connects up the beginning and the end, and the slope of that secant is b bar. The green lines are my tangent slopes. Remember, they kiss the curve at one point. And so where along that curve, we said the point at the mid-time, not the midpoint. Notice the midpoint looks like it's about 25. Midpoint's about right here. But that's not where the tangent equals the secant. It's the mid-time, which is in this case for this particular graph was 3.5 seconds. So 3.5 seconds, the tangent equals the secant. So we were finding a subtle point, but we were finding secant slopes. And trust me, this year I consider just blowing all this off and just telling you, maybe I should have, because it's really hard during this time to explain stuff. But this is a really good thought, and it's thinking like Newton. So that idea finally won the day. Said, okay, I'm going to go for it. We're going to go ahead and talk about it. I promise you this is probably the last time you get a chance to talk about it, because physics in college just blows right past which is very irritating. No wonder people struggle, don't understand physics, because you don't go through and show them where things came from. They really don't, especially engineering. Anywho, a lot of assumptions are. So because of that mid-time, the secant and the tangent slope are the same. That means that average equals instantaneous at that point. So I can then take each one of these steps, maybe the end of our class yesterday, I can collapse each step down to a dot. In other words, and 0, 0, of course, is the dot. So I'm saying that at that point, that is the exact velocity. And this is a little trick that Newton can use to, before he invents calculus, to kind of fool the data into saying it's instantaneous and not average. Okay. Because what Newton is obsessed with is these things being instantaneous. That's why he invented flux fields, as he called it. Okay. So then the next step, of course, is do a best fit line. And I will do that. Different color, go red. Got to go through 0, 0. You got no choice. The only point you know is right. Okay, so that looks pretty good. Yeah. Good enough, not great. That'll work. So I'm a little bit steep, maybe tiny. Okay, so now we look at this and we want to figure out its slope. Ultimately, remember, I'm trying to say what if I were to put that curve as one number to represent that curve, like one temperature to represent all the Brownian motion here. What is that one number? So blue, and okay. So now the slope. What is the slope of this? Slope of best fit equals what? What say you?
Yesterday we said 0.8.
We said 0.8. Okay.
Yeah.
Take a look. 4.5. Yeah, okay. Well, let me sure that's what we got today. Hold on, let me go back. Let me check that real quick. Make sure that's what we got. The other right. It doesn't sound right for some reason. Let me double check this. We said 0.76. Hold on. You sure that wasn't on the previous graph? The slope of the best fit here, if I go over 5, okay, if I go over 5 and then I come up, I'm going to hit right at 4, which, okay, 4/5. All right. About the same, 0.8. So the slope of the best fit equals, in this case, acceleration. And we're going to say that acceleration for this one, acceleration equals 0.80 meters per second because it's rise on a run. All right, that's how we left it yesterday, I guess. Okay, that's about, all right, so that's good. Good so far? Okay, so, then the next thing we want to do is we want to plot that. We want to plot, this is a trio. So we want to plot that acceleration. And you, on your paper, as they pointed out today, have no room. You have no room below, so you might have to kind of decide, but I'm going to change that for next year, so there's room there. Normally, we don't plot acceleration, but I'm kind of condensing it. We don't plot acceleration yet. I'm kind of condensing this. I like it condensed, actually. So you plot that, and that's sitting there right at 0.8. 0.8 And this is meters per second, and these are seconds. So the acceleration is not changing. So typical trio, flat, linear, parabolic, all right? As I go down below again at slope, go down here at slope. As I go up, it's area, which is integrals or derivatives. Derivatives for the slope, integrals for the area. Okay, so we talked about that, Now we go to the back of that sheet. Now, 1 through 6 is homework, but we'll talk about it enough where you don't have to worry about it. I mean, you'll understand it. We'll walk. You still got to fill it out, but all right. So this is the same graph as on the front. Only now I want to talk about a couple of things real quick. Okay, so first thing I want to do is draw a secant, draw the average. And we know that slope is 32. The secant slope is 32 meters over 9 seconds. So V bar equals 32 meters over 9 seconds. What does that equal to? 3.5, about, what is it? 3.5, right? 3.5. What's it? 2 seconds. 3.5 meters per second. Okay. Now, we know that at the that means that at 4.5 seconds, right here, 4.5 seconds, that should be parallel lines. I'm gonna change my color, but that tangent line, the green tangent line, is parallel at that instant to 3.5. So this is V at 4.5 is the same as average. Okay, but what I'm more curious about is the initial velocity is flat, 0 slope. The final velocity, we already know kind of from the front, because on the front, we did that, and on the front, we found that the final velocity over there was about 7, right? 7. So we go here and we do a slope of 7, and that's the final velocity. So right here, I'm going to guesstimate about 7. Okay, so that's the V bar at the end. Fine. Here's this. I'm going somewhere with this. So on the classwork, it says at the time, you can answer that, you can answer 8, you can answer 9, midtime, and now let's go to 10. 10 says we now have 2 new equations, or not really new, one of them's not new, the other one is though. 2 equations. First one is that the slope, the V bar is the slope of the whole thing. Well, that's simply rise over run. Well, it rises. Okay, it rises V bar. It's rising 32, or that would be considered delta X total, delta X tot, divided by tau. Now, who remembers what tau is? What is tau? What does tau stand for?
Total time.
Total time, right? So that's one definition of V bar. But now we have a new definition of V bar. V bar is the tangent line, the beginning V naught, initial velocity, and final velocity, V final, for that segment, divided by 2. Because this is 3.5, this is 3.5 here, this is 0, this is 7. Well, 7 divided by 2 is 3.5. So a new equation emerges that we're going to use to develop the orange equation. And that is V bar is V naught plus V final divided by 2. And this works on any, okay, these, by the way, this is only true, a caveat here. This is only true for parabolas. What? Oh. Okay. Sorry. Okay, only true for second order functions. Because the problem is students try and do these in quartets, and you can't. Only true for parabolas. Second order, not third order. Okay. Okay, that finishes that sheet. You look at the questions on the rest of the back to see they're easy to answer. Now I want to go to there, this one, 2.8. And we'll spend most of the rest of our time doing just the front part. We're just going to do a little bit on the front. We'll do this front half. This part. This is called the beautiful patterns. And it'll be on, you'll have, okay, so on the test, not the one before Thanksgiving, now I'm talking about the final, the one during finals week, you will be given this, and you got to fill the whole thing in. There's like 50 things there you got to fill in. It's like me asking a kid who's never doesn't know anything about numbers. I say, okay, I want you to tell me every number between 0 and 100, and go. So the kid goes, 64, let's see, 27, 13, and they sit there and hem and haw until finally they come up with all of them. That's dumb, right? Why not do them in order? And that's the same thing here. So students see this and they freak. They go, I got to know all that from memory? No, you got to know the pattern. If you can count to 10, you can count to 100, right? You just know the pattern. It's over and over again. Same thing on all motion. This represents, this is a solo, duet, trio, quartet. This represents all motion in the universe. All, not all, let's say 98% of the motion in the universe is on this, is going to be on this, like a periodic table, sort of, the Rosetta Stone of motion. All right. So let's start with something that's easy. I'm a big low-hanging fruit guy, as you know. So let's go with the old low-hanging fruit. Let's start with a duet. We've been doing duets since about day one in class. So those are called red equations, right? So I'll make red. Here it is X and V is my symbols. I'm plotting against time. In fact, I plot against time on all these. And you got to put units, not just, these are symbols, but if you don't put units on the test, you lose points. So seconds. I mean, on time, if you put seconds to be time, okay, I'm good. X, we'll do MKS, so meters, and then velocity, of course, meters per second. And then X is simply the red equation. So it's just, we'll keep it simple. Yeah, we'll keep it simple. So linear, and then this is flat. And so my equation then is just the red equation. So we have X equals, blow this up so you can see it. You guys need to, you need to let me know when you don't see things or I'm cutting out, or VT plus X naught. So that's just the red equation that's on your sheet or in the room, hanging in the room, but hopefully you have a sheet, or you have you have an equation sheet, right? It's on your equation sheet, which you should have printed out or else have it somewhere. I got to come up with a new equation sheet there too. The order is the power of the t. Well, that's just 1. T to the first, so 1. And then down here on the this one down here, we have simply v is equal to v naught. And the order is 0, t to the 0 power. By the way, I got to put this on here. By the way, anytime you go down on this, anytime you go down, there's a little black here. Anytime you go down on this, you go to the graph below, this direction, as you know, is for slopes. As I'm going down, this is the direction of slopes. Or we call them derivatives. And then as I go up the elevator, anything that goes up, I'll put it over here, true for all these, up, those are called areas or integrals. Anytime you go up. Okay, I'm trying to make it look nice. Up means area, like the finger dance. Area or integral. By the way, I extended the deadline for doing finger dances. I had 2 kids come in today at lunch to do the finger dance for me. I extended the deadline till after the Sunday after Thanksgiving, so like 29th or something like that. And you can send me a video of it. And this is from sheet, what is it, 2.5, something like that? No, 2.4 maybe. It's also on the take-home test, by the way. There's some finger dancing there. Okay. So let's do another easy one. Solo. Solo. There's no particular color that's associated with solo, so I'll just make it purple. So solo graph is just you sitting in your chair. Me sitting in my chair right now, my center of mass. And that is X versus T, and that is meters, and that is X equals X naught, very trivial, but sedentary lifestyle is what you do most of the time. So if you're sitting around, that's it. Okay, now let's get a little harder. We go to trios, what we're working on right now, right? So trios are considered orange. Orange trios, orange. We'll do orange from now to Christmas, a lot of orange stuff. So orange, we know that the first one is parabola. The next one is linear. And the next one is flat. And this takes care of a lot of your motion, if you're speeding up or slowing down. So let's go through and get all the details on that one. Oh, I made them go to the board on this trio. So now I'll stop. I'll give you a minute here. I don't want too much dead time. But you, on your own paper, in pencil probably, lightly do what you think it should be, and then we'll see if we're right. So all of you at home that are watching this, try it. I'll tidy this up a little bit. Now, if you're just sitting there waiting on me, you're blowing it, man. You're doing it wrong. Physics is an active class. You've got to have your hands active. Active hands equals active mind. Okay, so hopefully you have some idea. This is X, this is Z, this is acceleration. X is in meters, Z is in meters per second, acceleration is in meters per second. So we use that unit. Somebody asked in one of the hours to say, well, can I just use meters per second squared? Yes, that's a mathematical convenience, and I'm not saying I don't do it, but if you're a purist, you wouldn't say that. You would say meters per second per second. This meter per second squared is, yes, it does work out mathematically, but it provides a misconception. This, of course, is T, T, seconds. Easy points, right? Easy points on a test. Always get the low-hanging fruit on a problem. if you don't love, it's like pixie sticks. If you can't really work the whole problem, kind of pick at it for a while. Work a little bit, draw a good picture. Then maybe go, I think things are going in circles. The equation sheet says V is equal to R omega. Let me write that down. Maybe ask you will give me some points for it. And that's the same way you do the AP Physics exam. You go for, it's all those rubrics. And the AP Physics reader is reading that test, and they're looking for, did they write down V is equal to R omega? If you did, you get 2 points out of 15. Those are always worth 15 points, those free response. So if you don't, you go, well, I don't know how to finish it, so I'm not going to start. Oh, good luck. Because physics, you start a lot of things and you don't finish it. You start a lot of problems and you get stuck, but you keep fighting. I give you points for the fight. Anyway, so I don't know what I was talking about. So now let's go along here, keep going. Equations. Low-hanging fruit, right? A is equal to A naught. I can get that one. A naught. And then notice the pattern. 0 to 1. If that's 0, the t to the 0 power, that's order of 0. That's the order of 1. That's the order of 2. 0, 1, 2. Okay. But this is a parabola, right? And so we have x equals kt squared, like Galileo said, sort of. Galileo said x is proportional to t squared. But, you throw in a proportionality constant, you got it. Because that's all that is they've taken the proportionality symbol out, the little fish, and they replaced it with a proportionality constant, which is the k. All right, so we have this equation. Now, I want you to take a minute and write, if you haven't already, and write what you think that equation is. This is this equation for this graph right here. I made them do it in class. Made them suffer. And they had to guess. It's not really a guess. It's kind of here's what they said. They said, well, that is, it's linear. So a few of them said, okay, that is x equals VT. No. We're not plotting x. So that's a big no. It is, but here's the deal. Here's where you use a pattern. Okay, now you need probably a colored pencil, would be nice. But I'll use color here. This is why it's not so hard to count to 100 when you do it in order. It's not so hard to do these about 50 things here if you do them in order. Okay. This is that diagonal, you follow that diagonal. And there's a lot of things that that's the same pattern. You follow this diagonal. This should look familiar if you're a chemistry person. You do these kind of things on the periodic table, right? You can follow a trend, alkali metals, and then you can say, well, these things, they follow this trend down on D levels and P levels and things like that. And finally, we have this one. You can keep doing this. If we plotted the quintet and the sextet and all those, you can continue with this idea, this pattern. All right. So knowing this pattern, that helps, because that tells me that this equation right here is going to look a lot like this equation up here, only with different variables. Oh, geez. Why didn't somebody stop me, man? You guys are supposed to stop me when I'm getting tired. You got to stop me when I make a mistake. This should be x equals VT. X equals VT plus x naught. That's the right equation. I was thinking ahead. That didn't bother anybody? You guys have gotten, look, man, maybe sometimes I make mistakes on purpose, huh? Just see if you're listening. No, that was a mistake. And then you know what I do? They'll make mistakes on purpose in class, and then whoever catches it gets 5 points. Anyway, so this though, that's x equals VT. That must have really bothered you, unless you, of course, weren't thinking. X equals VT plus X naught. This one then is orange. You know what it is? Someone tell me. V equals what?
Would it be that?
XT?
Say again?
Go ahead.
Oh, I was just saying, like, was it XT maybe?
No X involved. We're on the velocity line now. Keep going.
Would it be that equation that we did on the previous page, the new one? The x or v naught plus v final over 2?
That would work on the graph above maybe, but yeah, okay.
Or is
What
that
you
just for the parabolas?
Yeah. Well, no, but what you said is true. That is true about this. That's not the equation I'm looking for, but I mean, I'm going to give you a point on that because you're right. That is true. I'll throw it in there, I guess. V naught plus V final divided by 2 is V bar. That is a true statement. But that's not the equation for the line. We're writing these equations in slope-intercept form. Y equals mx plus b. All right. So what's my slope? What is my slope of this line?
It's AT plus V naught.
Thank you. The slope is A, right? The slope is acceleration. Because as I said, when you go to the graph below, that's the slopes. Okay, the slopes lie beneath it. So then the basement. This is like the basement. So this is the ground floor here. And then, all right, so this is a 3-story building. Think of it that way. Yeah, so, yeah. This is a 3-story building. In America, we say the ground floor is the 0 floor. No, we don't. We say it's the 1st floor. In Europe, they say the ground floor is the 0 floor. And then the 1st floor is really what we call the 2nd floor. And so here, we're going to use a European model. We're saying for each one of these are like buildings. These are like buildings here. And that's a 0 floor, that's the 1st floor, 2nd floor, 3rd floor, like you would in orders. That there's a physicist that makes more sense the way the Europeans do it. Okay, anyway. So V here equals, like you said, AT plus what? Following the pattern.
V naught.
There you go. Now we're catching it. The V naught. AT plus V naught. So far you've got to memorize all of that, but keep in mind the pattern. You know, don't be the kid saying 53, 47, sofa, lady, TV. I memorized 5 words. Then you can brag about it for a while. I can remember those 5 words. Okay, so that's a joke that only somebody in the year 2020 would even get. All right, so now let's go to the quartet. Something we have not talked about. It's calculus, but now that we know the pattern, we should be able to solve it. So yes, we follow the pink diagonal order 0, 0, 0, 0. As a matter of fact, I'm going to step back and let you do it. Do the drawings. Do what you can. Okay, I'm not expecting everything. Fill in lightly in pencil, and you at home watching the recording later on, you do the same. Pause. Well, don't pause. I'll give you some pause time. And you try, and I made the classes, so if I make them do it, I'm gonna make you do it. Although I haven't figured out a way to make you go to the board yet. I need to learn how to use groups in Zooms. I don't know how to do group stuff. For some reason, I've got a mental block against using groups. Well, we got Bennett here today. That's good. Welcome, Ben. Bennett, since you come to class sometimes, and by the way, everyone's invited to come to class whenever you want. First, second, you pick your hour. You can come sit down in any class you want. Jackie was there today. She decided to come in and sit down in class, which is great. David Locke came in today, which is amazing. I mean, he works 70 hours a week, but he's found time to squeeze in and come into class and got a lot done. So yeah, if you wear a mask up and all, but if you ever want to come into class. Anyway, so Bennett, what I was saying was, I don't know if I put a slot for you on the porch since I see you in class enough. I think your stuff may still be at school. I'll go check that. Kind of what you want to do, Bennett. I mean, it depends. Would you rather me give you a slot on the front porch or just hold your stuff at school?
I can probably just pick stuff up at school because I'm there pretty often.
All right. Let's just do it that way. Okay, so hopefully I gave you enough time there. So here we go. Let's go down the list. It looks like the whole top row is X, and that's true. It's always, there's nothing. Someone asked once, well, what's above X? Like you keep going, can't you keep going up? No. How do I get, what's the integral of X? I don't know. X is the observable. So X, V, A, that's the A row. What goes below A? What's the slope of acceleration? You might happen to know this? Well, good. This makes me feel like I'm actually going to earn my money today. So the slope of acceleration is jerk, J. And J, lowercase j. Uppercase J, of course, you chemistry people know it's joules, right? And physics. Joules are joules. That is jerk. I didn't say J roof. It's not the unit vector J. It's lowercase j stands for jerk. And jerk is when you get, somebody comes up and pushes you in the back. That means that's a jerk. You trip and fall. You run into a wall, okay? You jump up real fast. You're at a stoplight, light turns green, you punch it. You punch the gas and you get whiplash. That's jerk. Somebody hits you from behind. That's all jerk. So yes, that'll probably happen to you at some point during the day. It could just be you jumping into bed or you stubbing your toe. All of those is examples of jerk. Okay. We're working our way through this. All right. So X then is meters. Please tell me I'm recording this. Yes. X is meters. V, the next row down, is meters per second, of course. Acceleration is meters per second per second. So what is jerk?
Meters per second per second per second?
Meters per second per second per second. Now we're being real purists, right? I mean, that is a purist, a physicist. If you're going to go around calling jerk meters per second per second per second. Eventually, even I give up. There's something after jerk called snap. And that's meters per second per second per second per second. And so finally you give in and just say, okay. So meters per second is also meters per second squared. That's a simpler way to say it. And meters per second per second per second is meters per second cubed. Now, you can prove this to yourself mathematically. Maybe we will later on. We didn't do it in class, but just a side note, there's a wrap-up special there. So I'll take either one. I mean, sometimes it depends how lazy I am. But the purist would say meters per second per second per second. Okay. Well, there we go. Now let's get our drawings. Of course, that is flat, following the pink diagonal. The orange diagonal tells me that is linear. It's just like these two. Sorry. It's just like these two. See, all these three are the same. And then this next one is a parabola. What would this guy be? What would this guy here be then?
Would it be like the same as a figure in like a cubed?
Yes, it's cubic. There's the point. So pulling in some zoom points today. Watch. Make sure you're writing these zoom points down. You get zoom points, Facebook points, discussion points. You guys can't really get discussion points, so you guys mostly zoom points. And there's some other point I was going to give you guys. Oh, I forget that. But look, if I'm looking at these three graphs, I can't tell the difference. So what do I got to do?
You put the dotted lines like.
I'm going to go with dotted. So that's dot, 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 dot. We make them dotted because that's negative time. And Logan said, third hour, he said, oh, okay. So negative time is the time before you start the experiment. Yes. Kind of like on a rocket ship, you say T minus 1 minute and counting, minus 1 minute and counting, right? It's a negative time. T minus 30 seconds. And then the clock starts when the rocket's engines start to fire. I need to say, I've never said that before. I need to say that in class. So let's, low-hanging fruit, of course. So let's do the orders. Order is 0, 1, first floor, second floor, 0 floor, ground level, first floor, second floor, third floor. And that's the order. Power of T. What's easiest next? The equation for jerk, that's easy, right? Just J equals J naught. So you might, someone asked this. They said, well, how much jerk can we experience this, like getting pushed in the back? How much starts to get painful? 5, 10, 15? About 2. The subways and trains have what's called jerk meters, and they're little accelerometers, but they put into that, and humans shouldn't experience more than 1.5 to 2 jerks. On a train starts to become irritating. I think roller coasters can't go above 2.5. You're not supposed to have more than 4.5 G forces, which is really associated with acceleration. You're not supposed to have more than 4.5 G's on a roller coaster, but you're not supposed to have more than 2 jerks either, because you do, you're on a roller coaster, after a while, that kind of gets tiring. It's all fun and games for a while, but then make it stop. And this, of course, is linear, so it's just like we follow these equations, right? We follow this equation, we follow this equation, and so this one's the same pattern. So now we're saying A equals, well, now what? What's the slope?
JT plus A naught.
Yeah, JT plus A naught. So now you're catching on, see? It's not like you're like the little kid. You don't really have to memorize 100 numbers. You just got to memorize the pattern to get to 100. And over here, the next one then, we follow the blue pattern. So that would be then V equals K T squared. Now this is a general K. Someone asked, well, is that K, is this K the same as this K? No, maybe coincidentally, but if they were the same, I would say K sub 1, all right? If you're talking about a specific constant, you say K sub 1, K sub 2, K sub 3, but this is just K, which is general. Finally, we have this equation. The last thing to do, we have this equation, X equals
KT cubed.
There you go. Got it. Whoever said that, give yourself a point. KT cubed. That's a cubic function. So that, my friends, are the beautiful patterns. I had a kid named Oliver, and he loved this stuff. He's a music major, but he took physics in college and he thought it was kind of cool. And he came back a couple years later to Mr. Askey. I mesmerized my classmates at a study session once, and I showed them this, and they all started going, "Oh, why didn't somebody show me this before? Kinematics makes so much more sense now." I don't know. They don't. This is my pattern. No one else has ever shown it. I don't think it's not in a textbook, but it is a way for you to remember all this different motion, and it kind of gives you a foundation to go, okay, I'm sitting here I'm at a cubic function, I'm in a quartet, what's the shape's going to be, that kind of stuff. I'm telling you, it really helps. Okay, so your homework, as far as we got in class, your homework is to do 1 through 9. I know you have the black and blue, and you have other classes, and you have the take-home test, but I'm saying don't spend more than 10 minutes, just 10 minutes familiarizing yourself with 1 through 9. In light pencil, try and answer a few of those. And then when we talk about tomorrow, it'll make much more sense if you've looked at it for 10 minutes. Set a timer on that. Don't go more than 10 minutes. Okay, and then we'll get to the hard stuff tomorrow here, and maybe get to 2-9. Okay. Very good. Any questions on the screen sharing before I turn it off? Okay, well, these things are getting to be as long as a class. Now I was about 56 minutes here in counting. IO, I now have your test as well. You saw that I'm sure you saw that, but it's on the front porch. So y'all come by and pick up your stuff. I'll leave it there forever, but just the longer it's there, and it's in a kind of a plastic thing, so it's not, it's a rain, it's covered up, but still, it's your test, it's your notebook. I don't want those things to get messed up. Some dog comes along, grabs it, and runs. I don't think that happens. I have a camera on it, so, but, okay. So, are we gonna say goodbye? Is that it?
What's your address again?
12 Carriage Lane. Whittier Middle School. There's those Victorian homes, right? North of Whittier Middle School. South of Alpine. Okay.
The black and blue.
Yeah, Io's been there. The Victorian homes on that 812 Carriage Lane.
For the black and blue, do we have to turn it back into you, or can we scan it or take a picture of it?
Good question. For test security, I want it back. Now, I want it back. If we're at the deadline, say it's 5 o'clock on Thursday and you can't get over here, then take a picture of it, send it to me. But still, I want it back. I want those papers back. I am teaching next year. I'm not saying next year's test is exactly like that, but I'll take some questions from it. And I would just rather it not end up in little brother's hands or something, or, somebody happens upon it. Kids don't do that really, but I mean, it does. I feel bad when a test, my take-home test fine, but in-class test, I would like to have a modicum of test security. I know they're out there right now, and you can copy all you want, but people don't think that way. It just sometimes ends up getting left behind, and then the kid sees it, and there's somebody coming over right now to go to the front porch. Who's that? Who's that kid? Oh, okay, that's her own. He's coming to get his stuff. Okay, so I will see you guys tomorrow, hopefully. All right, bye, y'all.